So now let's talk about the second derivative test. Recall that the second derivative gives us information about the concavity of the original function. And again, we're after the behavior, or analyzing the behavior of the original function. So the first and second derivative test are just tools to analyze some kind of function. So again, remember that the second derivative test is a test that gives us an idea of the concavity of the function. So the first thing we do is we look for critical values of the first derivative as a function. Okay, these are places where we may or may not have inflection points. Okay, if the second derivative does change sign before and after the critical values of the first derivative, then we have an inflection point, a change in inflection. That is, the function changes from concave up to concave down. All right. A nice thing about concavity of the function is it gives us an idea of whether the function has a minimum or a maximum in that particular region of the domain. Okay. So what we're after in order to find the critical values is we solve for the second derivative equal to 0, that equation, solve that for x. Okay. Or we're looking for where the second derivative does not exist. Again, this is analogous to the first derivative test. Okay? If indeed these are places where the function changes concavity, those are called inflection points, recall. And then we also, again, have to test the sign. Again, just like the first derivative test, even though these are places where the second derivative may be 0, or we have some kind of critical behavior, it does not guarantee that we actually have an inflection point. So to double check to see that it really is an inflection point, we have to test the sign. That is, if the second derivative of the function is positive for that particular x value, that means that the first derivative is increasing, so the function is concave up. And similarly, if the second derivative is negative, that means that the first derivative is decreasing, so the function is concave down in that particular region. So again, if the second derivative is positive, the function is concave up. If the second derivative is negative, the function is concave down. And you can see that a little bit more clearly when we look at a picture. Okay? I've drawn the tangent lines of the function at particular x values. And you can see that if we look at the tangent lines are here, it's negative here, it's flattening towards 0, and then it's increasing. So at least for this partition, before this little dashed line, for all x values from this dashed line that way, notice how the slope lines, or the equation, the tangent lines anyway, to the function are increasing, right? They start from negative and they go to 0 and they go positive. So they're actually increasing. You see that? So these slope lines are increasing as we go from left to right. So the first derivative is actually increasing, which means the second derivative is positive, okay, over here. So in fact, this is concave up. The function is concave up. So concave up. And on this portion of the domain, notice how I've drawn the slope lines again in red. The slope lines start positive, they go towards 0, and then they go negative as we go from left to right. Okay? So in fact, the first derivative is decreasing, or the slope is decreasing as we go from left to right. Okay? So f prime, the derivative, is decreasing, going down, which means that the second derivative is negative, as we see here. Right? Which means that, in fact, this is concave down. Okay? Remember that the derivative of something, the sign of that tells me whether that something is increasing or decreasing. Since the second derivative is the derivative of the derivative, it tells me that the original derivative as a function, if the derivative of the derivative, okay, if the derivative of the derivative function, if f prime of f prime, if that's positive, that tells me that the original function, which is the derivative, is increasing. Okay, this is how we make an analogy between the second and first derivative tests. And again, if the derivative of the original function, in this case, the derivative, if the derivative of the derivative is negative, that tells me that the original function inside here, which is the first derivative, is decreasing. Okay, similar. And this is, at least pictorially, what this second derivative test is telling you, okay, or the sign of the second derivative. And it tells you the concavity of the function. And again, if in fact we have that the concavity is changing sign, that is that if we look at the second derivative of the function, we find some kind of critical value of the first derivative, okay? And if we find out that it changes sign from negative to positive or positive to negative, that means it's changing concavity. And places where the function changes concavity have a special name. And remember, those places are called inflection points. So what we're looking for in the second derivative test is the inflection points of the function. And the sign of the second derivative tells me, in fact, the corresponding type of inflection I have, whether it be or concavity, that is, whether I have concave up or concave down. So if the function is plus the second derivative as a function, if I'm plugging x values in, if the second derivative as a function is positive, the function is concave up, and if not, it is concave down. Okay, that tells me the information of the actual original function. Okay, this is a lot of stuff to keep in mind, so let's do an actual example, and you'll see how this all comes together.